Hello everyone, this is Elisa Baum. I am GridGain Systems Director of Product Marketing. We'll begin in just a moment, but first I need to conduct some housekeeping. Could you please raise your hand using the hand icon in the GoToWebinar control panel to let me know if you can hear me okay? Let's see, do you guys hear me? I see hands, that's fantastic. Next, during this webinar, you will be on mute, but should you have any questions during the discussion, please enter them in the questions field within the control panel. At the end of the webinar, we'll take time to answer as many questions as possible, and those that aren't addressed will be answered in a follow-up blog entry on GridGain's blog. In addition, a recording of this webinar and links to the slides will be made available to everyone within 48 hours. With that said, I'd like to thank you for attending today's webinar, Apache Ignite and Apache Spark, where fast data meets the IoT. It's being presented today by Denis Magda. He's GridGain's Director of Product Management, as well as the Apache Ignite PMC Chair. And with that said, I will turn the floor over to Denis. Go ahead, Denis.
Thanks for the introduction, Elisa. Hello, everyone. And today, folks, we are going to discover one of the real use cases where Apache Ignite and Apache Spark both are widely used. Specifically, we are going to look into the use cases, IoT use cases, how both these technologies can help us to build IoT-enabled applications and infrastructure. Speaking about the agenda for today, first, before we start diving into the details of our IoT software stack, I want to briefly speak about the demands that are coming from IoT applications and services. Because once we know the demands, we know what exactly we need to build on the IoT side, on the side of our IT infrastructure. Next, we will, as for the IoT software stack, I decided to split it into main building blocks. First, we will start from the lowest level, which is their operating system that is usually deployed on your smart devices, on your smartwatches, on your sensors, or on your robots. Next, all of these edge devices, they measure information around their environment they are deployed in, and they transmit this information to our backend service, to our applications. And usually this is done via so-called data collection and enrichment layers, which will be our second building block in the software stack. Next one, we are going to briefly talk about the HTAP platform, which is our main storage and our computational platform. And by the way, HTAP stands for Hybrid Transactional and Analytical Platform. And when we are going to choose an operating system for our smart devices, or some framework for data collection and enrichment layers, or finally our HTAP platform, you must be sure that all this software provides all the APIs needed for our applications to be written and to perform well. And finally, I'll finish my presentation with a demo where I'm going to show you how you can quickly build a pretty simple application that will leverage from both Apache Ignite and Spark and you can use this template as a foundation for some of your applications in production. Okay, so, having said this, let's move on with their agenda. First, if to talk about the IoT demands to software, if you take a look at this picture, you will see that the IoT market is really broad. And specifically, here is when we talk about the things from this market or about the edge devices, we can consider a variety of different appliances or smartwatches or smart meters or robots. All these devices, all these edge devices or things, they are connected to the internet and they measure different information around them in order so that we can process them for our benefits. And what are the main demands that are usually coming from this realm? First one is real-time processing. Yes, it's true that it's not essential to to give or support any real-time processing guarantees for our smartwatches that are hanging on our wrists. But at the same time, if we speak about self-driving cars, this is where real-time guarantees are crucial and essential. For instance, as you know, many self-driving cars, they are equipped with a variety of with a myriad of different sensors and actuators, and all these sensors transmit the information around the road to the central processing system. And it's crucial for that system and for all the sensors to be able to transmit and to process this information in real time. Otherwise, something bad can happen. For instance, if a self-driving car cannot process some event in a couple of nanoseconds or milliseconds, then you can get in a car accident, which we want to avoid for sure. The next demand, that's about APIs. That's IoT. It's if to compare to other markets and then to other types of applications, IoT market is pretty young. It's not mature enough, but still, all the applications that are written for this specific task, they still want to leverage from standard and widely used APIs like SQL. So be ready if you work as a front-end developer or you work as a back-end developer for some IoT application, then most likely you would need to have some advanced querying capabilities. And usually SQL language is a choice for this. And furthermore, some of their IoT deployments, they work with geolocation information, like your location, some proximity. Like if to take a look into example, your smartwatches, if you want to transmit and process your location, then usually there are some special sensors deployed in your smartwatch. And if you want this smartwatch to transmit the data back to your backend service, we need to be sure that the backend server and the architecture that is deployed there is able not only to store this geospatial data, but also to tap into this data to produce some valuable outcome. The next demand is it's related for more advanced IoT deployments, more advanced IoT applications that need to execute some business intelligence tasks and some machine learning tasks. So it's optional. It might be optional for some of the applications and services, but anyway, our applications can evolve all the time, and it will be perfect to have such a platform at the core of our software stack that provides machine learning and BI APIs on top. Finally, usually this quality or this characteristic, which I call high availability, it's usually related. It's no longer kind of a good thing to have in our deployments. It's something that became the must. And here is it means that usually we can start with our IoT solution that, for instance, consists only of hundreds of sensors deployed somewhere. But over the time, your business can, grow, and you need to expand your overall deployment to thousands or dozens of thousands or hundreds of thousands of different sensors. And you want to be sure that your IoT stack, software stack, is able to scale along with your business growth. And even more, in addition to this scalability principle, we want to be sure that regardless what's going on with our IoT software stack, if some of our servers go down, we still want to be sure that our overall applications are up and running all the time, unless the whole data center goes down. But for this scenario, usually you can leverage several data centers, right? So, and if one of the data centers is down, then the other one will be up and running, and you'll be able to process all the queries from your applications. And yeah, we already covered the scalability principle. But here is, I want to point out that we want to have simple scalability. We want just we want to scale out our infrastructure on purpose easily. Just if you need to add one more extra machine to our cluster, I want to do this in a matter of minutes, not in a matter of days or hours. This is one of the things that worth keeping in mind. Okay, these are the main demands. However, and how our software stack might look like if you want to comply with these demands. That's kind of the IoT software stack that is described from the high level. At the bottom level, at the lowest level, we have device operating system or real-time operating system. And here is actually we have two choices. The first one is if your device is powerful enough, like if it has around 100 megabytes of RAM and hundreds megabytes of flash, then you can leverage from well-known Linux embedded operating system, for instance. At the same time, there are many of, like if we start speaking about the really constrained devices or really small devices like smartwatches or different smart meters, then usually they cannot benefit from Linux. Usually they are based on some really constrained hardware. And if to give you kind of an understanding of how the hardware can be constrained is, just imagine that a lot of different sensors and smart meters, they operate on hardware that has only, let's say, 100 kilobytes of RAM, just kilobytes, not megabytes, kilobytes, and a couple of megabytes of flash. And you are able to install a real-time operating system on that device. And even more, you will have plenty of resources to deploy your applications on top of that real-time operating system. Next layer that usually tightly coupled with the underlying layer is called data collection and enrichment layer. Here is usually we have some framework deployed, and this framework is connected to our sensors via some networking protocol, and this layer uses push or pull techniques to get the information from our IoT deployment. The next one, once the data enrichment and collection layer starts receiving the information from our devices, it needs to put this data somewhere. It needs to store this data somewhere. And here is, we want to offer you so-called HTAP platform as your storage and as your computational platform. And one more time, HTAP stands for Hybrid Transactional and Analytical Platform, which means that we want to use this platform for both OLTP and OLAP scenarios. And on top of that, we want to make sure that both HTAP, data collection, and real-time operating system, all of these layers provide the APIs needed, all the APIs needed for our applications to achieve the goals of your service or your business. And today I'm going to offer you to show you the IoT software stack that is fully built on top of their products and projects that belong to Apache Software Foundation. And again, starting with the lowest layer, here is we have our real-time operating system. Let's talk about real-time operating systems, because if you have pretty powerful hardware, you can tap into Linux, right? So we already mentioned this. But at the same time, if to speak about real-time operating system, here is we have only one solution that is available from Apache Software Foundation, the operating system that is called Apache Minute. And this operating system is kind of became the top level project in Apache, not that long time ago. And I'm going to give you a brief overview on the main capabilities of these operating systems in a minute. Next, speaking about the data collection and enrichment layer, here is we have much more options, guys. Like here is you can use Apache Spark, you can use Kafka, you can use Apache Flink or Apache Storm. or combine all these technologies together for the sake of getting and processing initial raw information coming from your sensors, coming from your, let's say, real-time operating system that is deployed on your devices. And once, let's say, and for this webinar, I decided to go with Spark. So, and once, for instance, if to talk about Spark, once you deploy Spark as your data collection and enrichment layer, Spark will be able to get the raw information from real-time operating system, from your sensors. It will be able to enrich it. Basically, enrichment means that you take some raw data and you add useful payload to it, like daytime. You can transform this data, and once the data is processed and transformed or enriched, you need to store it somewhere. And I'm going to propose Apache Ignite as your HTAP platform, as your distributed database, and as your computational platform that will keep all the data in a distributed fashion and will satisfy all the IoT demands and requirements we discussed a couple of minutes ago. And then speaking about the application APIs. Okay, and on this slide, I'm not exposing the APIs needed for low-level developers, though those developers who are going to write, who are going to program your smart meters or your devices. Here is I mostly will concentrate on the APIs needed for front-end and back-end developers. And here is you have two things. Since we decided to go for Apache Ignite and Apache Spark, then we will use the APIs provided by these two projects from Apache Software Foundation. Okay, now let's look into their every building block, every component we've chosen for their main software building blocks depicted on this slide. And we are starting with Apache Minute. Okay, so speaking about the Apache Minute, it's a real-time operating system. And what does a real-time operating system mean for you? First, that's an operating system that can run on really constrained devices. And a constrained device usually is powered by CPUs developed by ARM, like Cortex-M CPUs, or other CPUs provided by different manufacturers, like MIPS, for instance. And usually those CPUs can give you kind of several dozens or several hundreds Hertz. And next capability of Apache Minute. You as a application developer, you will be able, to get the main APIs that are needed for you to write your application. So for sure, you will be provided some multi-threading capabilities. You will be able to talk to your Flash-based file system if it's available on your microcontroller. And for sure, there will be some APIs needed to work with your sensors and actuators connected to your hardware. But at the same time, once all the information is processed locally or aggregated locally, there has to be a way to transfer it back to our data enrichment and connection layer. And here is Apache Minute provides a sophisticated networking library that is built, that is available as a part of the operating system. And you can use all these well-known Bluetooth, Wi-Fi protocols, and low-level TCP/IP or UDP protocols. It's up to you, the relative options. Next, when it comes to the deployment, it's required to have some security guarantees. Like if someone else can can hack you and get an access to your hardware, there should be a way to prevent any malicious software to be uploaded on your smart meters or your smart watches. And usually operating systems like Apache Minute, they provide some security guarantees, including secured bootloader that is able to verify the binaries that are being deployed on the hardware. And at the same time, when it comes to their software or firmware upgrades, for sure, you don't need to go to the factory, or you don't need to request all the smart watches to be delivered to you just for the sake of the update. You are able to connect to your edge devices, to your smart meters remotely. And usually all these capabilities, all this remote firmware and upgrade capabilities are embedded into their real-time operating system. And Apache Minute is not an exception here. Well, that's our low-level software that is used by system engineers and developers. Let's move on to the upper layer. And here is we have our data collection and enrichment capabilities. So here is I decided to use Spark streaming module as a middle layer between my smart meters deployed somewhere in the field, for instance, and my distributed database and computational platform that is to the right, which is Apache Ignite. So what Spark streaming does? Spark streaming is capable of receiving and processing streaming data in real time, and you are able to distribute the workloads and the processing across all the resources you have. This module was delivered to the market not that long time ago, but this is something that you can easily tap into if you just want to build data collection and enrichment layer for your IoT applications. And once Spark starts receiving the data from our IoT devices, it will be able to transform the data. It will be able to add some useful payload needed for your business use case. And once this task is over, it will be able to move the data further to your storage, to your Apache Ignite cluster. And let me just briefly take a look, give you kind of an overview on the storage itself, which is Apache Ignite. So Apache Ignite is a distributed database and a computational platform that is able to store data in both memory and on disk. This ability relies on so-called memory-centric storage. And the memory-centric storage implies that if you enable persistence, then all the data will be stored on disk for the sake of durability. But at the same time, you can store the full copy of data or subset copy of the data in memory, depending on your resources. And once you have a subset or the full set of data in memory, you are able to benefit from the in-memory performance. And the memory-centric also implies that this memory layer, it's not just a caching layer. It's a full-fledged storage that resides in memory. But once you combine together disk layer and memory layer, you can gain and benefit from both the durability of the disk and the memory performance of RAM. At the same time, as it's shown on this diagram, in addition to the Ignite native persistence, which is the default persistence layer in Apache Ignite, you are able to use some third-party database, like a relational database, Hadoop, or Cassandra. But there are for sure the differences among Ignite native persistence and a third-party database. For instance, if you now take a look at the APIs that are supported on top of our in-memory centric storage. For instance, if you highly rely on SQL capabilities, then SQL queries, in the scenario with Ignite native persistence, SQL queries will be executed over the data that is both in memory and on disk. But if you use some third-party database, like relational database, like MySQL or PostgreSQL, SQL queries will not be able to execute over that database. They will require you to have all the data in memory. Another difference between a third-party persistence and Ignite native persistence is that if by some reason your whole cluster goes down, then once you restart your cluster, you have to preload all the data from your third-party database in memory. Otherwise, for instance, if you keep using SQL queries and not all the data presents in RAM, then you can get incomplete and wrong result set. But Ignite native persistence doesn't have this limitation. After the full cluster restart, you don't need to wait while the data, you even don't need to preload any data in memory. You can start executing your SQL queries instantaneously, not waiting while the memory layer will be warmed up. That's kind of one of the differences, some of the differences we have between Ignite native persistence and Ignite third-party databases. Okay, so and speaking more about the SQL, about their about the APIs. So today I want just to look into the APIs that are relevant for our IoT scenario. But in general, Ignite provides you SQL key value APIs. Also, you can execute distributed transactions, execute so-called MapReduce-like computations, and deploy services and do streaming. And what's else new? What was added to the platform? You can deploy your machine learning models and run different machine learning algorithms. That's good, but so we do remember that on our first slide we had so-called high availability and simple scalability requirement. How does Ignite fulfill this requirement? The memory-centric storage that we've just talked about stores the data internally in so-called key value store. And for you, so key value store, you can think of a key value store as a distributed hash map. And that, as we know, we know how a hash map usually is built. The hash map consists of several buckets. And in distributed systems like Apache Ignite, we call a bucket as a partition. And here is we have our distributed key value store that is split into multiple partitions, and all these partitions are spread out evenly across all the cluster machines we have. At the same time, if to speak about the high availability, you can enable so-called replication factor, meaning that if you want to have at least one backup copy or two backup copies for every partition, you just need to turn on a special configuration parameter. And then, for instance, if we, let's say, have a partition A that is located on this node to the left, then this partition, this node will be a primary node for this partition A. But at the same time, since we turned on our replication factor, the same partition will be, the whole copy of the same partition will be available either on this node or on that node. Why do we need this? The answer is obvious. When this first node, and if this first node goes down, all the data that is stored in that partition will not be lost. It will not disappear, because the whole copy was available on some other node, and all your applications will switch to that node when they need to get the data residing in that partition. And at the same time, when we speak about scalability, simple scalability, in Ignite, probably it's one of the easiest tasks to scale your cluster. What you need to do, you just need to find a new server machine you want to add to your cluster, and you need just to add it to the cluster. That's it. After that, Ignite will automatically repartition some data so that the new node that joined the cluster also owns some partitions, and so that node starts processing workloads that are coming to Apache Ignite cluster. And next, if to talk about SQL capabilities provided in Ignite. Ignite, as you see, Apache Ignite internally uses key value store as a format of for data storage. But it doesn't mean that Ignite cannot execute SQL, well-known SQL queries. And even more, it doesn't matter actually what type of how your data is organized internally, unless you can index it properly, and unless you can store it in an optimized format. And Apache Ignite SQL capabilities are so broad and so powerful that there are a lot of use cases when Apache Ignite is used as a full-fledged distributed SQL database. And why is it so? For instance, here is at the bottom, we have the same Apache Ignite cluster that you could see on a couple of previous slides. No difference. Here is we have our cluster nodes that store the data sets spread out across the cluster of machines. And also, and in addition to the data, we all these machines store indexes. And the indexes are maintained in so-called B+3 data structure. And on top of this cluster, you are able to execute SQL APIs and well-known SQL queries such as select, update, insert, delete. These queries belong to data manipulation language specification, and Apache Ignite complies with ANSI 99 SQL specification. At the same time, when you need to, let's say, add a new index to your cluster in runtime, or drop a new index, or you want to add a new table or drop an existing table, you also can use well-known commands available in data definition language, such as create table, drop table, create index, and drop index. And you can execute all these APIs via native SQL APIs available for Java.NET and C++ developers. Or at the same time, you can use a truly cross-platform approach, which is based on JDBC or DBC drivers. Just connect from your favorite tool or from your favorite language and start interacting with Ignite by means of SQL APIs. And here is, and absolutely, that's SQL capabilities will be required for our IoT applications. Simply because it's unavoidable. It's unavoidable to have an application that doesn't need to execute some advanced queries. But when it comes to advanced queries, I cannot think of a better querying language rather than SQL that is capable of empowering us with this. Next, SQL is good, like key value APIs is good, but also if you store a massive amount of data in your cluster, sometimes we want to avoid data movement across a cluster of our networks. And here is we want to tap into their so-called collocated processing. Like collocated processing means that we know that some of the data, some specific data resides on dedicated machines in our cluster. And you can benefit from this knowledge and write special computations and send this computation to the nodes that owns a specific data set. And once you start sending all this computation to the place where data resides, you avoid data noise, data movement across your network. This is how you can underload your network and use the network for other tasks you have. Like on this picture, we have a pretty interesting scenario. Like Compute Grid actually Ignite it's Ignite's own map reduce or fork join framework. And the idea how it works is pretty simple and standard. Like when your application issues some computation, this computation can be split into a number of subtasks. And all these subtasks will be executed on the cluster nodes you have. And this way you can distribute the task execution. So you're going to use all the resources of the cluster you have, and you don't need to move the data over the network. And once every cluster node is over with its part of the computation, you will get a partial result to your application, and that will automatically reduce it in the final result set. This is how it works. Next, speaking about Spark APIs. So we mentioned that presently in this IoT software architecture, Spark is used as a data enrichment and collection layer. But at the same time, nothing prevents us from using Apache Spark further. Apache Spark and Apache Ignite have a special integration. Apache Ignite provides an implementation of Spark RDD abstraction, which allows to easily share state in memory across Spark jobs. So the main idea, or the main difference between native Spark RDD and Ignite RDD is that Ignite RDD provides a shared in-memory view on data across different Spark jobs, workers, or applications, while native Spark RDDs cannot be seen by other Spark jobs or applications. Like if you take a look at this picture, it means that Ignite shared RDDs, they are mutable and they're accessible and can be shared by all the Spark workers you have. Simply because these are just an extra API on top of Apache Ignite cluster. And Ignite shared RDDs, they are fully compliant with Spark RDD specification. All the methods implemented and available in Spark RDD are supported and implemented by Ignite shared RDDs. I'll show you today how you can just use those APIs directly from your Spark application. And one more benefit once you start using Ignite shared RDDs from your Spark applications is that you can run Ignite SQL queries that are much faster than Spark SQL queries, simply because of the way how we index the data. I was, to my knowledge, so the main reason why Ignite Spark RDDs, Ignite SQL query is still much faster than Spark RDDs is because first, Ignite has its own memory-centric storage. So we know how to optimize all our querying capabilities. And even more, you are able to index the data. You can define primary, you can define secondary indexes, and you can execute a variety of different queries, including joins, with joins using Ignite SQL. While this is something that is not available, something that is still missing in Spark. And this is how both technologies can collaborate together to give some more advanced capabilities to both Apache Ignite and Apache Spark users. Lastly, if to speak about the last API that might be needed for our IoT application, here we want to talk about machine learning grid. So this is required if you want to get more knowledge, if you want to do some research on the data that is stored, that is transmitted by your smart meters on your smart sensors into your Apache Ignite cluster. And today, Apache Ignite community is working on a special machine learning grid library. This library is still available in the beta state, but what's supported right now, we implemented the distributed core algebra on top of our compute grid and data grid capabilities. And even now, you can define different, you can work with matrices, you can do different calculations directly, writing your algorithms and logic on top of that core algebra module. At the same time, once that core algebra module was announced, the community started working on their basic distributed versions of the algorithms that are needed for this type of API. And we are working on the k-means clustering, linear or logistic regressions, and all the time you can expect to get more APIs and algorithms to be available in Apache Ignite. And presently, so the APIs are supported for Java and Scala, but at the same time, the overall goal is to make it available for other programming languages such as R, C++, or Python. So here is, I would encourage you to join the Apache Ignite community to try their, if you know that it's those APIs are needed for your IoT applications, and services. I'll highly encourage you to give a try to the APIs that are available in Ignite right now. And we look forward to hearing from your feedback, and probably you are will be interested to join the community and to develop some cool new distributed version of an algorithms and make it available for everyone who uses Apache Ignite for machine learning tasks. Well, before we move on with the demo, let me just quickly give you a view on what are the use cases that are supported by Apache Ignite and why we decided that that Apache Ignite is suitable for IoT applications. Like Apache Ignite, if you take a look at this diagram, Apache Ignite is used in a variety of segments and markets like financial services, software, telco, logistics, and travel. But at the same time, there are use cases from the IoT. To my knowledge, there are at least 2 customers that use Apache Ignite in the IoT deployments. The first one is ThinWorks, and the second one is Silver Spring Networks. And if we talk about the Silver Spring Networks, usually what the use case sounds this way. So this company deployed more than 50 million meters worldwide. And all these meters stream the data back to Silver Spring platform that is built and works on top of Apache Ignite cluster or GridGain cluster. So they use an enterprise version of Apache Ignite deployed in production because they were required to have some security guarantees. And again, all these meters, they are endlessly and continuously stream the data into the Silver Spring platform. And then the platform analyzes all this data to control optimal power coverage and usage of diverse territory. So you can think of it as, like, imagine that we have millions of power poles deployed in the United States. And then basing on the information delivered by the smart meters that are connected to those power poles, the Silver Spring network can transmit or control power usage, distributing the power from one pole to another, depending on the current consumption in specific on a specific territory. Well, and now let's take a look at our demo prepared for this webinar. So, as I said, I want to show you how we can just take Apache Ignite and Spark and how we can quickly build something workable and how we can stream the data from our smart meters, how we can enrich the data, and after that, how we can execute different useful queries over the data we have. So this here is I have that simple project. I want to start Ignite cluster on my local machine, and it's the simplest way is just to start it this way. I need to have a special configuration, and in that configuration, I just specified, I set up our networking component so that all the cluster nodes that are going to be studied on my local machine, they will be able to discover each other. Okay, so here is my first node is being launched. Let me start one more cluster node on my local machine. Okay, this node is up and running. And also during this demo, I want to show you Apache Ignite Web Console. That's our management and monitoring tool. I want just to track, I want to keep an eye on the state of my cluster machines deployed locally. So here is, where is it? So it should be, yeah, it's available over here. Let me connect to my cluster from this console. So actually Apache Ignite Web Console is available for everyone who wants to deploy it on premise or in cloud. Here is I am using the version of console deployed on GridGain's public domain. So this is why you see here is GridGain logo. But anyway, when you decide to deploy this console on your premise environment, you can customize it the way you like because it's available in open source. Okay, here I see that there are 2 server nodes running on my local laptop. There are some different metrics such as overall memory usage, CPU usage. The nodes are doing nothing at the moment, and this is why the graphs are pretty straight. Yes, the next interesting stuff. Now let's connect to the cluster from my Spark application. And here's those who have an experience with Spark. Here, as you can see, familiar lines in our code. Like here's I'm defining Spark configuration. I'm preparing Spark Java streaming context, doing some setups with my logger. And then what's interesting here is I need to prepare Java Ignite context. So in this Java Ignite context, I'm passing Spark context and also the configuration that configuration will be used by Spark workers to connect to my cluster. And once the Spark workers are connected to my cluster, I'm able to work with the data or stream the data or query the data stored in Apache Ignite using these references, sensors RDD and temperature RDD. Here is I have those RDDs defined in my applications. And if to go back, these 2 caches, here is we have caches deployed in Apache Ignite. They were deployed by my Ignite cluster nodes that were started earlier because they had all the deployment configuration needed in their Spring XML file. And now I just want to connect these caches. As you see, there is nothing stored in the caches at the moment. And what we will do first, Spark will try to preload some sample data into that, into my Apache Ignite cluster. We will generate some sensors, some fake sensors that are deployed in various locations. So here is we selecting latitude and longitude randomly. And we just add this data, we start processing it, and we save it into the Apache Ignite. Once you call this method, the data will be sent to Apache Ignite cluster. And finally, that will be the first step. Let's start my Spark application. While the Spark application is being connected, is being launched, the second method will do a different thing. Here is Spark will connect to some local host port number, which is 999. And from that port number, we are going to receive temperature information that was reported by those sensors. Like all this information will be delivered in the form of string. And we are going to split this information first. That's our raw data. After that, we are going to add some payload to this data, such as what's the date, timestamp of this measurement that was received by us. And finally, we are going to execute, we are going to save this temperature into Apache Ignite cluster. And all this chain will be receiving the data continuously and will push the data into the cluster. This is how the data will be processed, analyzed, and streamed in real time into our Apache Ignite cluster. Okay, so let's take a look at my Spark. So that exception is different now. We don't need to pay attention to it. This is what I will show you a bit later. Okay, here is I should see my Spark. Yes, my Spark application is connected as a client node, and it populated it's already populated my sensor cache. Where is it? Services and caches. Let me try to update the screen. Looks like something is glitching on a web console side. Okay, that's good. So here is we have 2,000 different sensors deployed by the application. And finally, let me start. Here as you saw that error. some error that is generated by Spark. This is because Spark cannot connect to my local host, so it cannot start processing the information from my sample sensors. But once Spark connects to this local host, it will start pushing the data to Ignite, and also it will execute this Apache Ignite SQL query. That's Apache Ignite SQL query that it can be executed over shared entities. And here is we want just to show the number of sensors, total number of sensors, sensor ID, and the number of times that sensor reported the temperature between 70 and 100 degrees. Okay, and let me start just quickly my final part, my sensor data generator. That's a kind of simple Java application that listens on this already known port number. And here is once my Spark application connects to it, it will generate some temperature in the range of from 0 to 110 degrees. And this information will be encoded in a string format, and it will be written to the Spark, and Spark will do the rest of the magic. Okay, so this Spark connected to this application. And now if we switch back to our Spark application, we can see that there is this exception disappears, and now we see a result produced by our SQL query. So there is a sensor ID, and the temperature and the number of times temperature between 70 and 100 Fahrenheit was reported by a specific sensor. At the same time, if you go back to our web console, here as we can see that this temperature cache is being populated over the time in real time. So this means that Spark is pushing the data into our Apache Ignite cluster. And even more now, we can execute, let's say, the same SQL queries from let's say from our other applications. And here is I just want to execute those queries directly from my web console. Like I want to see what the maximum temperature reported so far by all the sensors deployed by us. And I want to execute this query every second. Like the maximum one, here as we have it, 109 degrees. That's what we have. At the same time, as you know, Apache Ignite supports distributed joins, both collocated and non-collocated. And with this join, I want to to get maximum temperature that was reported by a sensor that is located in the United States. And these are the boundaries of continental United States territory. And here is what we have. Like, and we also can execute this query every second. So the maximum temperature was reported by sensor with ID 84, and that temperature is still the same. That unbeaten 109 temperature. It's actually the maximum one. Well, guys, that's all. That's how it's simple actually to tie up together Apache Ignite and Apache Spark, and that's how you can easily execute, how you can easily to connect to your smart meters. Here we just use some simple Java application, but in the real world scenarios, you will have some real-time operating system that is connected to your, let's say, Spark cluster and transmit data over Bluetooth or over Wi-Fi or over Ethernet. It's up to you. And you just can put together all these pieces and develop an application and solution needed for your application and needed for your requirements. So having said this, I'm ready to answer on the questions. Hope that we still have some time for that.
Okay, Denis, ready for the questions. And audience, if you have any questions for Denis, please go ahead and enter them in the GoToWebinar control panel in the question section, and I'll read them as we have time left. Okay, Denis, the first question is there only one backup node for each live node, or is it possible to replicate memory over multiple nodes for parallel processing purposes?
Yes, it's up to you. So you can have as many backups as you want. You just need to go to Apache Ignite configuration and increase replication factor depending on your needs.
Okay, next question. How would you recommend loading data into Ignite if the data is stored on AWS S3?
So there are different ways in Ignite. First, if you use Ignite has so-called data streaming API, and that API consists of Ignite data streamer that can push the data in the fastest way possible to your Apache Ignite cluster. For you, it means that you just need to write a simple Java application that will connect to your S3 storage, read the data from there, and we'll push it and we'll stream it into the Ignite. So you can find all the documentation available about that on Ignite resources. At the same time, if you prefer to use SQL, like insert commands for data preloading, we have some streaming mode that is available, that is supported for JDBC driver, for instance. And if you enable that streaming mode and start issuing insert commands into your Apache Ignite cluster, then our SQL engine will use the same Ignite data streamer for fast data preloading. So various options.
Okay, next question. Will Apache Ignite support data frames or just RDD?
Data frames, yes, the data frames, according to my knowledge, the data frames support should be rolled out by the end of this year. You can go to Apache Ignite dev list if you subscribe to it. You even find a special discussion around this feature. And I know that presently we have a prototype, and that prototype is being reviewed. And I hope their data frame support will be publicly available for usage pretty soon, in a matter of a couple of months.
Okay, next question. Any specific reason the demo uses Spark streaming instead of using Ignite streaming?
No, actually, so here I'm just decided to show you how you can leverage from different technologies and projects available in Apache Software Foundation. But anyway, in my personal opinion, Apache Spark streaming capabilities, they are kind of a bit more advanced than those provided in Ignite, because Apache Spark has been evolved as a streaming platform, like Apache Flink, for instance, while Apache Ignite is being evolved in a direction of a distributed database and computational platform. And sometimes streaming capabilities provided by Apache Ignite might not satisfy all the requirements you need to implement in your scenarios. And here is when you can leverage from both, for instance, Spark and Ignite, combining both projects in your applications.
Okay, next question. This is a follow-up on the replicated nodes question. Are those nodes visible under the compute grid or only provisioned for backup purposes?
All the nodes in Apache Ignite are equal, meaning that there is no any pure backup node, for instance. Like when you increase a replication factor, it means that if one node can store a primary copy of a part of the data set, and at the same time, it will store backup copies of other data sets. Which means that once you get this kind of distribution, when every node stores both primary and backup copies of the overall data you have, your computations sent from the compute grid will be distributed as well automatically. Hope that this answers your question.
Sorry about that. I didn't realize you weren't done speaking. We have time for a couple more questions. So the next one is, does Ignite provide periodic snapshotting commits capability during data load?
So speaking about the snapshots, so if you enable Apache Ignite native persistence, then technically you will be able to do full cluster data snapshots. But presently in Apache Ignite, we have only interfaces that you have to implement to achieve this capability. However, GridGain as an enterprise level provider of Apache Ignite deployments implemented distributed snapshots capabilities, and you can use them for your deployments. If you need like to make a cluster-wide snapshot while you are preloading the data or while you are deciding to upgrade to the new version of your software, you can use snapshots capabilities available in GridGain. Like you can do full incremental snapshot, full snapshots, incremental snapshots. You can even do so-called point-in-time recovery when we take a full snapshot, incremental snapshot, and a write-ahead log file, and we will be able to roll back a cluster to a consistent state.
Okay, well, this brings us to the top of the hour. There are several other questions. What I will do is put them together and get them over to Denis, and he'll work on a blog post to address some of those with our blog owner. So with that said, I'd like to thank everyone for attending today's session. I hope that you found it insightful. I'm thinking with all the questions, you found it very informative, and we're glad for that. Please join Denis in the near future. He will be doing a two-part series called Essentials for Developers and Architects, and it will provide advanced coding examples. The first one will be in November, and the second one will be in December, and that information is on gridgain.com. We'd love to see you in a future show. With that said, Denis, thank you so much for a great performance, and we hope to see everyone in the future.
Thanks, Alisa. Thanks, everyone, for joining me today. Hope to see you soon. Bye-bye.